So yes, very exciting day. Last day of new material in calculus. So we're talking about section 9.10. We're talking about the representation of functions by power series. The representation of functions by power series. We talked a little bit about that idea yesterday, right? The idea that in order for it to be a function, we had to talk about its domain, and that's where that interval of convergence comes in. Okay? So I want you to do this. Recall the sum of a convergent geometric series. What does the sum of a geometric series look like?
A sub 1.
A sub 1.
Over 1 minus r.
Over 1 minus r. Excellent. And tell me about r.
It is.
Okay, it is a common ratio. Yep, its absolute value has to be less than 1, right? Can't be 1, it can't be greater than 1. Okay, so we're going to go through this exercise to get your brains working. Suppose a sub 1 equals 2 and r equals 1/3. Generate a series. Okay, so instead of giving you a series and ask you for the sum, I've given you the first term and the common ratio, and I've asked you to write the series. Okay, so give me some terms in this series.
2.
2.
2/3.
Plus, how'd you get 2/3?
2 times 1/3.
2 times 1/3, right? Because that's what you do in a geometric. You're multiplying by that common ratio over and over again. So what's the next term look like?
2/9.
Yes, which means you're really doing 2 times 1/3 squared, right? One more, 2 times 1/3 cubed, and so on. And the general term for that would be the sum from n equals, we'll go from 0 to infinity, 2 times 1/3 to the n, right? Okay, so we're going to take this same idea and we're going to create some more generic power series. Okay, so I want you to do this. Suppose a sub 1 is 1 and r is equal to x. Generate a series and find its sum. Suppose a sub 1 is 1 and r is x. Generate a series and find its sum. So let's generate the series just like I did in the previous example. What is your first term? 1. Plus, what is your second term? X. Plus, what's your third term? X squared. Plus, what's your next term? Except it's not.
Sorry.
Okay. Right, so this is the sum from n equals 0 to infinity of x to the n. And then if I'm supposed to find its sum, tell me what other restriction I'm going to... Actually, you know what? Let's do this. Don't do that yet. Yes, you're right, but don't do that yet. Let's write the sum. Let's write the sum of it. Okay? 1 over 1 minus x. Huh.
Oh, that's similar to something.
Well, it's one we've done before. Right? We've done that series before. We said it's one that AP likes for you to know. But we arrived at that series in a different manner than we did before. How did we arrive at that series before? We just did a Taylor polynomial. You guys that are telling me LNs and antiderivatives, that's when we manipulated it. Okay? But when we came up with this originally, we did it using the Taylor polynomial. We found the derivative of it, right? And we evaluated that derivative at 0, and then we found the second derivative and evaluated it at 0, and then we plugged it into the big Taylor polynomial form. Okay? Well, and there's nothing that says that you can't do that anymore. However, it can also be done this way. If you see this as a geometric, if you see whatever you're given as a geometric series where you have a sub 1 over 1 minus r, then you can generate the series this way. And you don't have to go through the process of creating that Taylor polynomial with derivatives. Are you with me?
Mm-hmm.
You mean to say that again? Yes. Okay. 1 over 1 minus x is in this form, a sub 1 over 1 minus r. This, by definition, is the sum of a geometric series. If you have a constant divided by 1 minus anything else, something, then that is a geometric series. And I know that geometric series are created by taking the previous term and multiplying it by the common ratio. Okay? So you could create it that way. You could say, well, if I know this, the first term's 1, so the second term is x, the third term is x squared, the next one's x cubed, because if it's a geometric series, I'm just multiplying by that common ratio every time. So I could do it this way rather than having to take the derivative each time. And on the quiz, lots of you missed this one because of the chain rule, right? This is really, if you were doing it the old way, this is that, and when you take the derivative, it's that times -1 because of the minus x. So that made all of the terms come out positive, which indeed they are. Okay? So you could continue to do it this way, but for some of you, your brains work differently, and you may see this, and this may be much easier for you. Okay?
So you can only do that when your variable has an exponent of 1, right? So say like that was 1 over 1 minus x squared.
Actually, no, but let's do some examples. The important part is the 1 minus. Now, if you had a negative, you could make it minus a negative. I mean, if it was plus.
Yeah.
So that's what we're going to do next. I'm going to show you some examples where you can take what you're given and manipulate it so that you put it in this form. Okay? Yes, Elise?
So then, like on that one, if it would have been, will there be one that says it's a center at a different place then?
Yes, and
Okay,
that's
so
where they
then you
get...
just put the x minus 2 or whatever it would be, or what would you do?
I'm going to show you one. That's kind of the hardest example you get with these. Okay, and by the way, I do have to say at this point, now that I've calculated the sum, that the absolute value of x would have to be what?
Less than 1.
It has to be less than 1, right? In order for this geometric series to converge, because that's what it is, that r, which in this case is x, has to be less than 1. So what does that mean my interval of convergence is? -1 to 1, right? Because this means x less than 1 and x greater than -1.
Why do you not have to test?
Why don't I have to test the endpoints? That's a really good question.
Because
That would make it.
Because why, Kevin?
undefined, yeah.
Natalie?
Because when you plug one into the sum, it would make it the sum undefined, right?
Hold on.
These values right here, no matter what they are, since this is geometric,
It'll always converge.
it would make it, if the endpoints, whatever they are, would make it be 1, right? It would make your ratio be 1. Whatever your endpoints are would make the ratio be 1. I mean, that's what I set it up to be. And it can't be 1 and be convergent. So the moral of the story is, if you're ever doing a problem and you're asked to find interval of convergence, and that problem ends up being geometric, do you ever have to waste time substituting in the endpoints and testing it the way that you did the other day? No, you don't, because you don't have to include them. You would never have to include the endpoints on a geometric.
Because it's making it less than.
Because when you plug in these endpoints to the series, it will make it 1 to the n or -1 to the n. And your first homework problem last night, or your number 11 in your homework last night. This was number 11 in your homework last night. 1 to the n, that diverges, right? Because that ratio is not less than 1. The geometric says that's going to diverge. This one, -1 to the n, that's also a geometric where it's not less than 1. So it will diverge. And I mean, I even drew out some numbers. I mean, this one you're continually adding 1. This one it's fluctuating between -1 and 1. So depending on where you stop, that determines your answer. So that one could not. Okay, so that's why. That's why you don't have to include the endpoints.
So if you ever get a 1 as your solution, it will diverge.
For geometric.
Why only for geometry? I'm sorry, I'm not asking.
Okay, the rules for the geometric test. Okay, your geometric series test that we learned in 9.3.
Yes.
The only way a geometric series will converge is if r is less than 1. Because remember, you're multiplying by that term and then adding it to the previous one, right? That's what you're doing in series. So if it's bigger than 1 or it's equal to 1, you're always increasing it. Or it's at least staying the same. Where if it's less than 1, you're decreasing the previous term. And if you're decreasing what you're adding each time, you will eventually approach some value. Okay? All right. Okay, so let's do another example. This is going to kind of address Derek's question. Find a power series for f of x equals 1 over 1 minus x squared, centered at x equals 0. Find the first 4 non-zero terms and the general term. Find a power series for f of x equals 1 minus x squared, centered at x equals 0. Find the first 4 non-zero terms and the general term. So one way you could do this is you could build a Taylor polynomial, right? You could take the derivative of this 3 times, since they want the first 4 non-zero terms, and substitute in 0, and then you could plug it into that formula for a Taylor polynomial, right? Or you could recognize that it fits pretty nicely into this whole idea of a sub 1 over 1 minus r, right? Okay, so if you see it as that, what is a sub 1? 1. What is r? X squared, right? R is what follows the minus sign in the formula, right? So generate a series based on this information. What's the first term in this series? 1. how do you arrive at the next term? You multiply by the common ratio, which is x squared,
It's x
plus,
squared.
then you multiply, right? Because then you just multiply by the same thing again, don't you? And you multiply by the same thing again, right? So how do you write the general term? There's my first four non-zero terms.
From 0 to infinity.
N equals 0 to infinity of x squared to the n.
You can write out that like, if we can just get the a sub 1 equals 1 r equals x squared, just go immediately to the series.
You can immediately go to the series. And that's why this is nice. Like if you recognize it as a geometric, it's a lot faster and a lot easier than going through that whole creating of a Taylor polynomial. Okay, now what do I need to attach with this?
X squared.
X squared has to be less than 1. Question, Michael?
Yeah, so like if we realize that it's like the geometric, it's always gonna be like the ratio to the n power.
Yes, absolutely. Okay, so I want to show you something I forgot to do a second ago. Okay, so let me go back up here because I wanted to show this to you. This is based on last night. Okay, so remember up here we came up with the interval of convergence is from -1 to 1. Okay, so what this means is if I graph this in y1 and I graph this in y2, it's only going to be the same where? From -1 to 1. Okay, I want to make sure you understand what that interval of convergence is like. Okay, so here I'm going to do it. There's 1 over 1 minus x, and then I did this out to the 8th power. Okay, so there is the graph of 1 over 1 minus x. And then here comes the graph of the polynomial. Okay, is it even addressing this?
No.
No, it's not even taking that into account at all. Where's the vertical asymptote?
X equals 1.
At 1, right? Okay. So then if you want, you could add another term. If I add another term, what's the only thing that's going to change?
The direction.
The end behavior, right? It's going to come from the other direction. Okay, so you can see it starts to veer off out here. And you could look at the table. Oops, it's still graphing. You could look at the table, maybe. Oh, I'm pressing the wrong thing. Oof. And you can see I'm pretty good, but then now look at your differences.
Why are they different from that?
Why are they what?
As you get closer to when you go back. Oh, it's -1.
Well, remember, at 1, that's your asymptote. But remember on the graph, on the real graph, it then comes down. But on your polynomial, it stays up there.
Okay.
So see, at 1.1, the real graph is down here at -10. But on the polynomial approximation, it's at 15 point something.
So from -1 to 1, they have all the same y.
Yes, so -1 to 1 is your interval of convergence. Okay? All right, just I want to make sure we're good there. Okay, let's do another one.
So So is the integral one conversion on that still just -1?
Yes, it is, -1 to 1. Thank you.
You do that by saying like x squared is less than 1x.
Yes, you say x squared is less than 1 and x squared is greater than -1. Okay?
So but then how do you, like then every time x squared, like you would square root -1, right?
Yeah, so this is x is less than, on a quadratic inequality, the best way to solve those is graphically. Okay? So, yeah. So it would be greater than 1, or less than 1 from here to here. Quadratic inequalities work differently. You can't set them up like the linear inequalities that you solve. You have to find the intervals on which it works. It's generally just easiest to graph them. Okay, here we go. Find the power series. We're going to do 2 more and then you are done.
For life.
Find the power series and interval of convergence for the following. And the first problem is f of x equals 1 over 4 plus x. Okay, so they've given me a hint. They've said power series, okay, as opposed to Taylor polynomial. Remember that Taylor series, it is a power series, right? But it does say power series instead of Taylor. It doesn't mean that you have to do it my way. It doesn't mean that you have to do it this particular way that we're doing, trying to make it look geometric. You could do the old way and set it up as a Taylor and simplify it and you'd be fine. Okay? But you can manipulate this thing to make it fit into this form, 1 over 1 minus r. I'm sorry, a sub 1 over 1 minus r. Okay, I can manipulate it so that it fits that form. What would you need to do to begin that manipulation process? Pull out a 4. Take a 4 out of the denominator, right? Because that now makes this what? 1 plus 4 over x? Okay, remember, I want to make it look like that. So what am I going to do with that 4? Oh, did I write it backwards? I was wondering why y'all are all looking at me.
It's like 16 over x.
Sorry, I wrote it backwards. I was wondering because I was getting these blank stares. I'm like,
All of us are.
x over 4, thank you. Better? Okay, all right, so what can I do now? I can put the 4 up top, right? And make that my a sub 1. And then what can I do here? Because I need it to have what kind of sign? A minus sign. So I make this minus negative x over 4. And voila, I have it. A sub 1 is 1/4. R is negative x over 4, right? So all I have to do to create the series is write down a sub 1, which is 1/4, and multiply it by right? You're not a fan? And then multiply the 1/4 by that thing squared. And then multiply the 1/4 by that thing cubed, right? So the series can be written as 1/4 times negative x over 4 to the n.
Do we
You
don't
can stop here because you don't have to simplify for purposes of AP. But if you don't like the way that looks, right?
Squares. X squared.
What's wrong, Natalie?
Okay, so, like, I understand, let's see, so the a sub 1 equals 1/4, r equals negative x over 4, and then my brain doesn't like having to write out the 4 terms, I just wanna go to the series, like, writing out the terms, I don't know, it makes sense, but it confuses me kind of.
Okay?
So when would we have to write out those terms?
When they tell you to.
When it's like the 4 non-zero, whatever?
Yes.
Okay.
Yes.
And then if they tell you, like, in this example.
And by the way, I do have to say this too. Sorry.
It's okay, but then in this particular example, they don't say anything about that, so I could just go to the series and it wouldn't be
Yep.
problematic.
If they just wanted you to write the series, yes. They generally don't do that though, just to let you know. They always want a few terms. Okay, so I know this, I know negative x over 4 has to be less than 1, and negative x over 4 has to be greater than negative 1, so negative x is less than 4. Switch the sign. Right? So what's my interval of convergence?
Negative 4 to 4.
Okay, so some people really like this. It's very easy for them to convert it to this form of a sub 1 over 1 minus r and generate the series. Okay? And I want to show it to you because some people really can do that. It's also a time thing. Yes, sir.
Are you done with that, or do you need?
I am.
Do you need?
Well, it's the same general term right here.
Because you still can't have those ones. You still can't have those ones.
What do you?
Like, do you need to plug in the inputs
Oh no, because it's geometric,
because it's geometry?
right? We said because look, if you plug this into the series, you have created a 1.
Okay, yeah.
Right.
Okay.
So that's why I don't ever have to do it. It's not wrong if you do. It's just that whatever you plug in there is going to create a 1.
Yeah.
So yeah, it will diverge. Okay, one more. You probably really won't like this one, Derek.
Yeah.
Okay, when you say that, are you recording and that's why?
What?
Derek, I think I know Derek, I thought you were talking about Derek Kling, and I was so confused.
No. He a while ago said, I don't like this.
Yeah. It's got little intricate things.
He doesn't like it.
So is this the whole page?
Well, I'm just going to write kind of big. Centered somewhere else, okay? And I gotta tell you that if I saw this and I was supposed to come up with a power series, I would do a Taylor and just simplify. That would be me, because my brain doesn't automatically go to this. And I think it takes a lot more practicing and doing for your brain to go to this, but I'm gonna show you just in case. Okay, so the difference is I'm now centered somewhere else. But my goal is still to make it look like a sub 1 over 1 minus r. Okay?
It's already set up that way.
What?
It's already set up that way. It's just that it's set.
Well, but I'm centered somewhere else now. Okay, so I've got to incorporate this center into this. Okay? So I'm going to take this and I'm going to create an equivalent statement, but I'm going to center it at negative 1. Okay, so I'm going to go 1 over 1 minus, and in place of that x, I'm going to put x minus negative 1, right? Because it's centered at negative 1, it's always x minus c, right? Now this becomes plus, but when you distribute that minus, it becomes minus, so what do I have to tack on here to keep it equivalent to that?
Negative
Negative
one.
one.
Not another negative one, a plus one. Right? Remember, this and this have to be equivalent. I'm just trying to change their, the way they look. So I put in my x minus c, and when I put in x minus negative 1, this became plus, but when you distribute this minus, it makes it minus, so I have to put a plus 1 there to cancel it out. So this is now equivalent to this, right? But I just need it to come out in a different form. So it's now going to be 1 over 2 minus x plus 1. And then I need to take out a 2. So I'm going to have 1 over 2 times 1 minus x plus 1 over 2. Now where can I move that to? Up to the top. So I have 1/2 over 1 minus x plus 1 over 2. Am I in the form a sub 1 over 1 minus r? Yes. What's a sub 1? 1/2. What's r? X plus 1 over 2. So let's write out a few terms. So this is 1 over 1 minus x, centered at negative 1, will be equal to 1/2 plus 1/2 times x plus 1 over 2 plus 1/2 times x plus 1 over 2 squared, and so on, right? So that's going to be the sum from n equals 0 to infinity of what? 1/2 times x plus 1 over 2 to the n, where the absolute value of x plus 1 over 2 has to be what? Less than 1. And then remember, I've also been asked to find the interval of convergence, right? So I need to say x plus 1 over 2 is less than 1, and x plus 1 over 2 has to be greater than negative 1. So x plus 1 is less than 2, which means x is less than 1. X plus 1 is greater than negative 2, which means x is greater than negative 3. So my interval of convergence is negative 3 to 1. Do I have to test the endpoints? No. Why? Because that is a geometric. What's my radius of convergence? 2. How do you know that? Because I was centered at negative 1. Okay? So what that means is if I graphed this thing centered at negative 1 and then I graph this polynomial, the only places where they will be the same, they'll share the same y values, are from negative 3 to 1. Yes?
If this were an AP3 response question,
Yes.
Would the actually writing of x plus 1 over 2 is less than 1 and x plus 1 over 2 is greater than negative 1, would that be a point by itself, or would it just be getting the final?
It would just be getting the interval. I'm just showing that because I think some people forget how to solve absolute value inequalities. Okay, so let me pass out the homework sheet that goes with this. Yes. Yes.